Okay, let's unpack this. Today, we are taking a deep dive straight into the engine room of modern artificial intelligence.
Hmm.
We're not talking about the high-level ethics or philosophy. We are tearing apart the foundational architecture, the speed secrets, and, the actual mechanics that let these models scale up.
Right. Our mission today is all about the how. We're drawing on material from some really deep technical courses, think Stanford CME295, to understand the clever engineering that makes LLMs, well, fast.
And scalable and controllable,
Yeah,
especially at inference time.
exactly. You are going to walk away from this understanding precisely why your favorite AI chatbot behaves the way it does.
Okay, so before we get into all the new stuff, we have to do a quick reset on the transformer architecture. It's the foundation for literally everything we're about to discuss.
Sure.
And when you look at transformers, there are really three main buckets. First, you've got the old guard, the encoder-decoder models. T5 is a classic example.
Text in, text out. Great for things like translation.
Then you have the second category, the encoder-only models, like BERT. These are, they're phenomenal for understanding context, for classification.
And this is a really crucial distinction now, by modern definitions, BERT isn't really considered an LLM because it doesn't generate new text sequentially. It's for representation.
Which brings us to number three, the architecture that just completely dominates the field now, decoder only.
Yep. That's your GPTs, your llamas, your gemmas.
They're the backbones of basically every generative model you use. They work by just predicting the next word, the next token in a sequence. Pure creative machines.
And that L in LLM is doing some really heavy lifting. When we say large, it's not just marketing. It means three specific things. First, model size.
And we're talking about models with at least 1 billion parameters, but often hundreds of billions.
And there's data size. The training data is just colossal, sometimes measured in, tens of trillions of tokens?
It's mind-boggling. And the third factor is compute. The sheer GPU power needed to train these things was initially just gargantuan.
Though inference, actually running them, is getting cheaper.
Right, and that's mainly because of the optimization tricks we're about to get into.
So let's do it.
Let's jump right into that scalability challenge. If you have a model with hundreds of billions of parameters calculating every single forward pass, running an input through every single one of those parameters for every token, it's just economically crippling.
It is. It's an immediate architectural roadblock.
Yeah.
And the solution is, it's brilliantly simple in concept. Don't use all the parameters all the time.
And this is the idea behind the mixture of experts architecture, the MOE.
Exactly.
I love the analogy for this. Think of a huge research department with 1,000 experts, a mathematician, a chemist, a historian, whatever.
Mm-hmm.
If you have a question about algebraic geometry, you don't send a memo to all 1,000 people.
No, of course not. You'd send it to maybe the 2 or 3 math experts who can actually answer it.
And that is exactly what MOE does. There's a small, dedicated network, they call it a gate or router, and its only job is to look at an incoming token and decide which specialist subnetworks, the experts, should process it.
And critically, modern LLMs use what's called sparse MOE.
Sparse MOE. Okay, so what does that mean in practice?
It means we're only selecting the top K experts, where K is usually a really small number, like 1 or 2.
Just 1 or 2?
Just 1 or 2. So this is how you get these incredible efficiency gains. You can build a model with 1 trillion potential parameters, like the switch transformer, but if your router only selects 2 experts to do the work, you're only computing on a tiny fraction of the total model.
So we're trading, 100% computation for maybe 2% computation per token? That's an insane scaling lever. It's an engineering marvel.
It really is.
But there has to be a catch.
There is. But before we get to it, we should probably clarify where this all happens in the model.
Okay.
MOE is almost always placed inside the feed-forward network, the FFN layer of the transformer block.
Wait, why there specifically?
Yeah.
Why the FFN?
Because that's the biggest computational bottleneck. The FFN accounts for something like 2/3 of the computational weight in the whole block. So if you want to save the most compute, you put the experts there.
Maximize the savings. Makes sense. Okay, efficiency achieved. Now, what's the inevitable training problem that comes with this?
The catch is routing collapse.
Or routing collapse.
During training, the router can get, for lack of a better word, lazy. It might find that 1 or 2 experts are consistently pretty good for all tokens, and so it just keeps sending everything to them and ignores the rest.
So those other experts just atrophy. They become useless.
They become completely useless, which defeats the entire purpose of building this massive sparse model in the first place.
That sounds like a disaster if you've just spent millions building a trillion parameter model and 90% of it is never used. How do engineers fix that?
They get very clever with the loss function during training. They add an extra term that basically penalizes the router for not spreading the work around.
Ah, so it encourages a more uniform distribution.
Exactly. It encourages exploration. They also use other tricks, like noisy gating, which is a bit like dropout. It injects a little randomness into the router's choices to make sure it doesn't get stuck in a rut.
So that handles the scaling. Let's shift now to the moment of truth generation. Once the LLM has processed everything, it outputs a raw probability distribution over its vocabulary. How do we turn those probabilities into the actual words we read?
Okay, so we have three main strategies here. The first, and by far the simplest, is greedy decoding.
Greedy decoding.
You just pick the single token that has the absolute highest probability at that exact step. That's it.
If it's the most likely word, why wouldn't you always just pick that one? Isn't that optimal?
It's only locally optimal. It's not globally optimal. Think of it like choosing a path. One path has a 90% chance of being good right now, but it leads to a cliff. Another has an 80% chance, but it continues on smoothly.
Greedy decoding would take the 90% path every time and walk right off the cliff.
Precisely. It can't look ahead, so the sequences can end up being nonsensical. Plus, it's totally deterministic. Same input, same boring output every single time.
Okay, so to fix that, we have method 2, beam search.
Right. Beam search tries to find that globally optimal path. It does that by keeping track of the k most probable paths. K is the beam size across multiple steps.
It's like searching a maze with, say, 5 flashlights instead of 1.
That's a great way to think about it. And it's why it's still the standard for tasks where you need high precision, like machine translation.
But you never see it used for conversational AI. Why not?
Well, a few big drawbacks. First, it's way more computationally expensive. You're tracking k paths at once. Second, it has this weird tendency to favor shorter sentences, so you need these complex length normalization fixes.
It's still not very creative.
Exactly, it still lacks diversity. If you want creativity, you have to introduce some randomness.
Which brings us to the gold standard for creative LLMs, sampling.
Right. Here, we choose the next token randomly, but it's weighted by its probability. So if the word "the" has a 70% chance of being next, it'll get picked about 7 out of 10 times.
So that gives you the diversity, but you have to control it, right? You don't want the model pulling some super unlikely word out of nowhere.
For sure. So we filter the pool of choices. The simplest way is top K sampling.
Just ignore everything except the, say, top 50 most likely words.
Yep. The sampling only happens from that small list.
And then there's the more sophisticated version, top P sampling, or nucleus sampling.
Nucleus sampling is smarter because the size of that pool is dynamic. It samples from the smallest set of tokens whose combined probability adds up to some threshold, P.
So if P is 0.9, you're only looking at the top few words that make up 90% of the probability.
And that means the pool is bigger when the model is uncertain, giving you more variety, and smaller when the model is confident, making it more conservative. It adapts.
This is where it all comes together. The crucial knob that regulates all of this is the temperature hyperparameter.
Temperature is so important. It operates directly on the raw scores from the model, and it's basically a dial that shapes the final probability distribution. It decides if you get a factual report or a wild poem.
So let's say I'm a developer. I'm building an LLM for, I don't know, a coding assistant. I want predictability. What do I do with the temperature?
You set it very low. A low temperature close to 0 creates a really spiky distribution. It shoves almost all the probability onto the single best token.
So it becomes deterministic, very conservative.
Perfect for factual tasks.
Okay, and if I'm writing a fantasy novel and I need some bizarre plot twists?
Then you crank up the high temperature. A high T flattens the distribution out. Suddenly, words that had a low chance are much more likely to be picked.
The output becomes more creative, more diverse, and, well, a lot more unpredictable.
A lot more.
It's so interesting that the core transformer architecture is fundamentally deterministic. The weights are fixed, the math is the math.
That's right.
So the sampling process, controlled by the human user's choice of temperature, is the only source of non-determinism in the whole thing. That one variable is what separates a coding assistant from a poet.
It's where the user's intent meets the model's potential.
Okay, let's talk speed. At inference time, even with MoE, there's still a problem. LLMs are usually memory-bound. They spend more time waiting for data to move around than actually doing the math.
Absolutely. So optimization tricks are vital.
Yeah.
The foundational technique here is KV caching.
KV caching.
So remember, LLMs generate token by token. For every new token, the model has to attend to all the previous tokens. And that means recalculating the key, K and value V representations, for every single past token, every single step. It's massively redundant.
So KV caching just saves those pre-computed K and V values in a cache so they can be reused instantly. No recalculation.
It's a huge win for speed, a fundamental optimization,
But it creates a new problem, right? A memory problem.
a massive memory problem. As context lengths grow into the millions of tokens, that KV cache just balloons. And if you naively reserve memory for the maximum possible context length for every single user, you waste so much GPU memory.
That sounds like an operating system problem, not an AI problem.
It is. And the solution comes from computer science. Page attention.
Page attention.
Used in systems like VLLM, it manages the KV cache in fixed-size blocks, just like memory paging in an OS.
So instead of reserving a whole empty overhead bin on a plane for one person's small bag, you're just giving them exactly the space they need, block by block.
Perfect analogy. It drastically increases memory utilization, so you can serve way more users on the same hardware.
And beyond just managing the memory better, engineers are also shrinking the size of what we have to cache in the first place.
Right. The first trick is group query attention, or GQA. This just reduces the number of key and value heads you need to store by grouping them. Less to store, less memory needed.
And then there's a more aggressive method.
Yeah, latent attention, which you see in frameworks like DeepSev-V2. This actually stores compressed representations of the K and V vectors. It's like zipping the data before you cache it.
A much smaller memory footprint.
For sure.
Before we move on, we have to mention the ultimate speed hack. Speculative decoding. This uses two models.
It's such a clever idea. You have a small, very fast draft model that quickly guesses the next few tokens.
It just proposes a sequence.
Right. Then the larger, slower, more accurate target model checks all those proposed tokens at once in a single forward pass.
So if the small model guessed right, the big model confirms several tokens at once, and you've basically generated multiple words in the time it usually takes to generate one.
Exactly. And if it's wrong, the target model just corrects it and you move on. But you still get massive speed ups on average. It's a game changer for latency.
Okay, let's move from the engineering of speed to the engineering of input the prompt. Models can handle huge contexts now, millions of tokens, but there's this phenomenon called context rot.
Context rot, or the needle in a haystack problem. It's simple. The longer the context you give the model, the worse it gets at finding a specific piece of information buried deep inside.
The noise just overwhelms the signal.
Pretty much.
Which means prompt structure is absolutely paramount. An effective prompt usually needs four things: context, instructions, input, and then, critically, constraints.
Constraints are so important for controlling the output format, like forcing the answer to be invalid JSON. That often relies on a technique called guided decoding, where you filter the model's output to only allow tokens that fit the required structure.
And within this whole paradigm, you have in-context learning, ICL, which is basically teaching the model on the fly. You start with zero shot.
Just the instruction and the input.
Versus the more traditional few-shot approach, where you give it a few examples of input-output pairs before you ask the real question.
Historically, few shot was always better. But that's changing.
Oh, really? How so?
With today's really capable models, a well-crafted, super detailed zero-shot instruction can often perform just as well, or even better, than a few-shot prompt. The quality of the instruction is becoming more important than the number of examples.
And to really unlock that reasoning ability, we have techniques like chain of thought, COTI.
COTI is basically mandatory now for hard reasoning tasks. You force the model to write out its step-by-step reasoning before it gives the final answer.
And the big win there isn't just better performance, it's also debuggability.
A huge win. You can actually see where the logic went off the rails.
And the final layer on top of that is self-consistency.
Right. Self-consistency builds on COTI. You just run the same prompt multiple times with sampling, so you get multiple different chains of thought.
And then you just take a vote?
You take a vote. It's majority voting on the final answers. If 3 out of 4 reasoning paths lead to the same answer, that's probably the correct one. It makes the final result much more robust.
Yeah.
You know, this deep dive really has spanned the full cycle, from scaling innovations like MoE through the generation mechanics like sampling, down to these critical efficiency tricks like KV caching and page attention.
And the prompting.
And the prompting. It really shows that the secret to modern AI isn't just one big breakthrough. It's this relentless layering of really clever engineering.
And that leads us to a final provocative thought for you to consider. We've established that the model's core logic is deterministic. The math is the math.
Hmm.
But its creative output is dictated entirely by the human user's choice of the temperature setting during sampling. If the model can be perfectly precise and factual at t=0 and wildly creative at t=1, is the real utility of these models less about their own inherent intelligence and more about our ability as users to precisely regulate the randomness needed to solve a specific task?